Okay, so acid-base balance, just introducing some pretty basic concept, no pun intended. Thank you. No pun intended. First thing I want you to know is chemistry was a prereq for this. It's just a question of how long ago was it when you took chemistry? Did you use your high school chemistry to satisfy the prereq, or did you take a high school chemistry? Well, so I'm going to give you a quick review of acid and base and buffer chemistry, and I mean quick review. How many of you remember learning about buffer systems in chemistry? And wasn't that fun? Was that your favorite part of the semester? Because I hate buffer systems. Hate it. Now, luckily for us, the most clinically important buffer system that we're worried about in the human body is this one. This will be your responsibility to know this reaction. What does it mean in chemistry when you have double-sided arrows? It is reversible. It can go one way or the other. Good, awesome. Let me tell you what you're looking at. This is hydrogen ions. I know they are not free in solution. They form a hydronium ion. I'm not going to keep saying hydronium ion. I'm just going to say hydrogen ions, okay? Okay. This is bicarbonate. It is an anion. Hydrogen and bicarbonate can combine to form carbonic acid. Carbonic acid can dissociate into CO2 and water. Conversely, CO2 and water, which are byproducts of cellular respiration, can form carbonic acid, which in turn can dissociate in the other direction into hydrogen and bicarbonate. This equation is another way to calculate pH. The original way you probably learned to calculate pH was the negative log of hydrogen ion concentration. And I will show you that equation tonight, but that is not the equation we will be using on your lab exam, nor on lecture 4. We will be using the Henderson-Hasselbalch equation. No, not Michael Hasselhoff, Henderson-Hasselbalch. Are we paying attention? This equation is your responsibility. It states pH equals the pKa. That's my job to tell you what pKa means. Its value will never change because we're only playing with this buffer system. The value for pKa for this buffer system in our body is 6.1. It's my job to tell you what pKa means tonight, and I will never test you on it. Then we're going to take the log. We're going to divide the bicarbonate by the CO2 values. Bicarbonate is the base. The base always goes in the numerator. CO2 is the acid you should pay attention to tonight and next week. It always goes in the denominator. It is my job to explain to you what this 0.03 is. And be careful, because later on in this PowerPoint tonight, I'm going to show you a slide where I show you 0.3. And I'm showing you two different things. When I come back to this equation in just a little bit, I'm going to tell you the classic mistakes students make on their lab exam using this equation, because this is the first step in those 20 points. And if you do not calculate correctly, poof, go all the points. So when I explain this equation and how to calculate pH using it, and when I tell you the dangers, the classic mistakes, I want you to pay attention, because I really don't want you to lose your 20 points. Lab Unit 2 should be a really happy time, because I'll explain something to you right now. In your grade sheet right now, Your 2 lab exams, the big ones, lab 1, lab 2, are worth 20% of your overall grade. And in that 20% category, you have 1 lab exam that you've already taken. And if you did poorly on that 1 lab exam, that 1 grade entered in that column is having a weight of 20% on your grade. When you take lab 2, if you do really well, 2 things happen. Now that first lab exam no longer has 20% effect on your grade. It's now down to 10. And lab 2 counts for 10, and you can offset the bad lab exam. So there is a chance to come into grace with lab 2. Pay attention. 20 points where it's clear as day what's coming to you and how to answer. Where else have you been on campus where you've had that kind of invite? Like, I invite you to do well on the exam. Let me tell you how to get the 20 points. Please pay attention. There is a lot in this PowerPoint. That's why I'm starting it tonight, which is some basic fundamentals. An acid. For our class, our perspective of what an acid is something that will dissociate a hydrogen ion. Look, carbonic acid dissociates a hydrogen ion. It's an acid. Acids come in different strengths. There are strong acids and there are weak acids. We don't care about that in this class. We don't care. We don't care. What is a base? A base is something that can take the hydrogen ions that are in solution and bind to them again. Let's look at this equation again. Bicarbonate, remember, is your base. It can bind to hydrogen to create carbonic acid. Bicarbonate is a base. It's really good at saying, come here, hydrogen ion, you're so lonely, come back and bind to us. We are your conjugate base. This was the pH scale that you probably remember from chemistry, and the equation you used. pH equals the negative log of the hydrogen ion concentration. You will want to bring your computer, looking at my computer to make sure it's working, your calculator next week. Your calculator should have a log button to it. You want to bring yours because I will teach you how to use your calculator with that log button. And believe it or not, if you have a Casio or a Texas Instrument, and depending which model of Texas Instrument you have, it likes the values entered in that equation on the first slide that I showed you, entered in a certain way. Order, properties, property of orders. Orders, no. Thank you. That one, I'm like, what is that I'm trying to say? Order of operations. That's one of the biggest problems on that equation that students make. They forget their order of operations. Do you remember yours? Do you know what I'm talking about?
Yeah.
Do I need to sing to you?
Yes.
Okay. Thank you to my school, my high school. I went to a private, all-girl Catholic high school. Sister Mary Cara. Sister Mary Beth Muir made us sing before math class every day. After we said our decade of Hail Marys, we had to sing our order of operations. Here we go. I am not a vocalist. Please excuse my dear Aunt Sally is a riddle we all use. P is for parentheses, E for exponents too. Multiplication and division, addition and subtraction. If you follow all the rules, you will get yourself out of school. Ooh, 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 please excuse my dear Aunt Sally. And then we had to do it in a round. And yet my kids go, Mom, PEMDAS. I'm like, what? PEMDAS. No, please excuse my dear Aunt Sally, is a rule that we all use. No, Mom. Don't do that again. Number one mistake is order of operations. Now, the old pH equation. None of this you have to do. None of this you have to do. But back when I went to school, we weren't allowed to use calculators. Can you imagine? Taking SATs without a calculator. Let me just get out my... We had to learn how to do logs based on just memorizing log tables. It was awful. So, Tyler, how many moles of hydrogen ions do we have in our blood, you might ask? 4 times 10 to the negative 8. Great, let me take the negative log of 4 times 10 to the negative 8. Well, Tyler, I can distribute, just like dealing cards, the log function to everything in my parentheses. I can take the negative log of 4, and I can take the negative log of 10 to the negative 8. Now, 4 can be written, Tyler, in many different ways. It can be 4 times 1 or 2 times 2. Let's use 2 times 2. And I can distribute the negative log to each of those 2. So I am going to take the negative log of 2, which is negative 0.3, and then the negative log of the next 2, which is negative 0.3. And then I'm going to take the negative log of 10 to the negative 8, which is 8. 8 plus a negative 0.6 gives me 7.40. Our body fluid pH. Are you impressed? Okay, now math back to you. What will happen if that number doubles? If we get twice the amount of hydrogen ions in our bloodstream, what is a doubling of that number? Or what would happen if that number was cut in half? We have half the numbers of hydrogen ions. What is that number when it's doubled? That's right, 8 times 10 to the negative 8. And if it's cut in half, 2 times 10 to the negative 8. And I can still use that negative log pH equation. And I can get a viable range, 7.1 to 7.7. That range reflects us going from roughly doubling our hydrogen ion concentration to cutting it in half. And I'll remind you, our pH scale is an inverse scale. The lower the number, the higher the hydrogen ion concentration. The higher the number, the lower the hydrogen ion concentration. 7.1 to 7.7 is roughly our viable limit. It is actually a little bit bigger than that, but for us, I want you to think 7.1 to 7.7. Now, on your lab exam, you're going to have 2 acid-base problems. And Kate, in some of those questions, after you calculate a pH for your patient, I'm going to ask you, what kind of acid-base disorder is your patient in? How can you best help your patient? What kind of kidney, renal compensation would you expect to see in your patient over the next 2 days? I'm going to ask you those questions. I'm going to tell you how to answer them. Kate, if you calculate a pH in your patient of 28, you've done something wrong. Why would I give you a patient that is clearly dead?
Great question.
Kate, if you calculate a pH of -2, you've done something wrong. You will have a patient in viable range. Do you hear me? Do you hear me? If you calculate a pH out of normal, viable range, you have, and if it's extreme, like if you calculate 28, and I get answers like this. That's why I said, who volunteers to lose all 20 points? Raise your hand. I don't want you to. If you do not calculate a pH in normal range, again, 7.1 to 7.7, it's actually a little bit higher than that, a little bit lower than that, but that's a good estimation. If you calculate -2 or 2 or 28, 14, 19, it's not viable. You have done the equation incorrectly. You have calculated incorrectly. Check your order of operations. In your nervousness, did your big meaty finger poke too many buttons? No, that happens. It happens. Did you put the acid in the numerator and the base in the denominator? Did you not multiply by 0.03? Did you enter 0.3? Because you're going to get a pH that is out of normal viable range. Are we clear on that important concept? Okay. Sorry that I'm wearing my squeaky sneaker shoes, but I broke my heels walking back and forth on campus today. So I had to put on my tenny go fasters. So you might be thinking, Matthews, where do these acids come from? They come from our cells during normal cellular respiration. We do make hydrogen ions. We make other acids too. Lactic acid during anaerobic metabolism. Keto acids like from Unit 2, beta-hydroxybutyrate, acetoacetic acid, and other forms of ketone bodies like acetone. Remember that from Unit 2? The issue is once the cells make those acids, then the pH inside your cells can get away from normal range. And proteins denature when the pH isn't maintained in homeostasis. So what do the cells do? They go vomit, and they get all of those acids out of them and into a different body fluid compartment, your plasma. Okay, now your plasma proteins are at risk of becoming denatured because now your plasma pH is going to deviate possibly out of normal range. That's not okay. I am going to tell you how your plasma is well suited to handle these acids until you can get them out of your body. So let's talk about ways to get stuff out of your body. What are all the ways to get stuff out of you? What are your modes of egress? Pee, okay, there we go. Breathing. Defecation. Sweating.
Vomiting.
Okay, vomiting. Saliva. Tears. Yes? Huh? What? No. Oh, come on.
All your holes.
All your holes. Okay. Yes. Thank you. Okay, earwax. That was not the hole I was about to go to. But okay. Because someone from another class, a guy, of course, ejaculation! And I went, yes. And then I made the mistake of saying, so out of all of those, what do you do the most? I went, don't even tell me the same answer again, because that's creepy. What do you do the most of? Breathing and urination, or at least making urine. Remember, every minute you're dripping about 2 milliliters of urine into your bladder. That's a pretty fast drip rate if you think about it. So those 2 ways are the fastest ways to get these acids out of your body. The problem is when you're breathing, you can only get out volatile acids, ones that can go into the gas phase. And that's CO2. CO2 is an acid. Excuse me, Kara, you said CO2. You said an acid has to dissociate a hydrogen. Well, go back to that equation I showed you, where water and CO2 can form carbonic acid, and then in turn that dissociates a hydrogen. So you see carbon dioxide is an acid. Trump, you need to listen to me on that one. It is an acid. It's a weak acid, but it's an acid. Any other acid that's not volatile has to come out in your urine. We call those fixed acids. Okay, well, the problem is if you're talking about acids that are coming out in your urine, well, we would prefer it not to burn when we pee. Do you agree? Because your urine can get to be a pretty low pH, like 6, sometimes lower. That's pretty acidic. And you don't want to be like, and not want to pee. So we need buffer systems to neutralize the acids that are coming out in our filtrate. And the classics are phosphates and ammonias. Now, I do not go into those two pathways. In pathophys, we spend a lot of time talking about excretion of acids, titratable acids versus fixed acids. I do not go into that in this class. Take patho if you're dying to know that answer. I just want you to know that your renal system, your tubular, your nephrons have the ability to help neutralize those acids so it doesn't burn when you pee. Proteins are also very important buffer systems inside your cells and even in the plasma. They are your most abundant buffering system. The most abundant. I'm sorry, Kara, then why did you impress upon us on slide 1 that reversible reaction saying that that was a very important buffer system? Well, because it's not the most abundant, but it is the most clinically important one. Clinically important. So here comes a red blood cell to have gas exchange with that tissue bed that you're seeing in the top left corner. Those cells are making CO2 and water as a byproduct of metabolism. And here comes the blood to drop off oxygen and pick up the CO2. Well, how does it pick up the CO2? One way, 1 out of 6 ways, is that it will pick the CO2 will diffuse into the plasma, diffuse into the red blood cell. Within the red blood cell, carbonic anhydrase, which is an enzyme that facilitates the hydration to CO2, CO2 and water, forming carbonic acid. This reaction does not go spontaneously very well. It requires an enzyme. And these red blood cells have that enzyme. Inside the red blood cell, carbonic acid dissociates into hydrogen and bicarb. Oh no! We just took a weak acid and we converted it into a strong one. Kara, what are you thinking? Take it easy. The hydrogen is going to go to a very abundant red blood cell protein and bind to it. And that protein is going to neutralize it. That's called hemoglobin. Now, I'll show you exactly how hemoglobin does that next week. So it's okay. Oh no! But now we have a base. And the pH inside the red blood cell is going really, really high. The red blood cell's like, please stop being so dramatic. We'll just put the bicarbonate out in the plasma. Oh no! We just lost a negative charge and we must maintain charge balance. The red blood cell says, sweet, I'll just bring in a chloride. It's called a chloride shift. Now the bicarbonate is out here and you're going, and now my plasma compartment, the pH is going up because I just put a whole bunch of base out there. Oh, but we're forgetting all of the other acids, like lactic acid and keto acids that I just listed that are also in the plasma, and that base is going to help neutralize them. So that base is actually quite important. All is okay. And when this red blood cell gets to the lungs, we're going to reverse this. Bicarbonate comes back in, hydrogen comes off, they recreate carbonic acid, it dissociates into CO2 and water, CO2 comes out of the red blood cell into the alveolus. and out goes your CO2. It's reversible. So your lungs are going to get rid of that CO2, the volatile acid, and the kidneys, they're going to have to get rid of your fixed acids, the ones that aren't volatile. And next week, will learn exactly down to the molecular formulas, how your kidneys do that, and where in the nephron. Where matters. So there's a lot of fun to be had next week. It's pretty intense. And I've got 5 minutes, so hold tight. I'm holding on to my promise. I see you all looking at the clock. I'm trying to give you 20 points, and you're looking at the clock. You're still going to get out early. No, you're not. So this reversible reaction, it can swing one way or the other. When will it shift left? When will it shift right? Stand up, sit down, fight, fight, fight. Which way will it go? And, okay, we'll tackle that. But first I want to go back into chemistry and ask you, do you remember Le Chatelier's principle? The isohydric principle? Don't remember, none of that ringing a bell? Le Chatelier's principle, if I act it out to you, says if you've got a reaction in equilibrium, and if you introduce into that system more reactants, the equilibrium will shift so that you create more products, right? You're gonna find a new equilibrium, I guess is what I mean. The equation will shift, the reaction will shift. You'll get a new equilibrium. And in chemistry, we're like, I don't get it, I don't understand it, I just know I have to balance my equation. If I get more here, I'm going to get more over there. Actually, Le Chatelier's principle has been part of our class since the first week. Yes, it has. Le Chatelier's principle says in chemistry, if you disrupt a system, it will try and find a new equilibrium. We've been talking about that all semester long. We just use different language. Homeostasis. If you disrupt it, if you have a deviation, the system will try and correct to go back toward set point. It's Le Chatelier's principle in physiology. That's what it is. It's homeostasis. So don't let that language scare you. It's getting back toward set point. That's all we're talking about. How can I shift this equation to get back towards set point? And this is what I'm going to teach you in the last 3 minutes I have. Focus. This is so important. Acids and bases neutralize each other. Acid, base, they want to neutralize each other. Good? Acidosis in our class will be anything below 7.40. We know from week 1, our normal pH range is 7.35 to 7.45 for a normal pH range. Do not confuse that with viable limits. For testing purposes, we will stick to a hard in the middle number, 7.40. So anything below 7.40 is acidosis. Clear? Anything above 7.40 is alkalosis. And I mean anything above. 7.41, alkalosis. 7.39, acidosis. That's how tight I want it. Now, how can you have acidosis? If acids and bases want to neutralize each other, how can you have acidosis? 2 ways. You can either have too much acid, do you see that? Or too little base. But either way, they're not neutralizing each other anymore, are they? Okay. Let's say you have acidosis from too much acid. What's the acid? What's the acid? Carbon dioxide. That's the one that we're making the most of. Okay, so so hydrogen is an acid, don't get me wrong. But in the Henderson-Hasselbalch equation, the acid was CO2. Remember, it was in the denominator. So that's our acid, okay? So if I have too much acid, what is that? Too much what? CO2. Okay, you're making too much of it. You want to neutralize this. What do you think the compensation should be? Make more bicarb. That's your base. Good. Reset. How can you have acidosis the other way? Too little base. What are you going to do? How do you reach equilibrium again? Le Chatelier's principle. What are you going to do to compensate? Get rid of the CO2. Okay? Reset. One of those two things, the acid, CO2, or bicarbonate, the base, one of those is going to be the problem that started the shift. The other one will be out of normal range, reflecting the compensation. Okay? In your problems next week, both will be out of normal range. One will be the instigator of the problem. The other one shows the compensation. And in the last 30 seconds, I'm going to put on the board your normal values for CO2 and bicarbonate. Because for you to know if they're high or low, you have to know normal values. And here they are. When you're done writing them down, goodbye. Normal values for CO2 are 35 to 45 millimeters of mercury. Normal values for bicarbonate are 22 to 26 millimolar. Those are the normal values. Yes, that's your responsibility to know. You have to know those normal values. Have a great weekend.